Okay, the application of matrix calculus, continuous beams and continuous frames. Work of Dr. V. Lewe from 1915. This is an extension to this work as proposed by Reynolds-Bienge based on quantum mechanics understanding. So what Lewe has done in his theory is to take the point of loading to the nth degree within a concrete ceiling. But you can take that point of loading to the nth degree at the point of infinity within that point of loading, and what you discover is the point where it cannot be extinguished further, that the load that's being carried by the beam results in an instability somewhere, and that instability occurs at the meter 4, the second moment of area within the beam. Now, it's a piece of matter, and so therefore at the center of this piece of matter we can analyze the bending that's taking place within the atom in which this second moment of area, the inertia, occurs, around which the bending occurs, and it creates a permanent instability. Now you'll see at the end of Lewe's theory, his dissertation, he gives us a beautiful diagram. This one. And this is the conclusion to his works. So what I've done is I've just opened that out and those little diagrams to show what's happening when you look at it two-dimensionally from above. So that in here he's showing condition 1, equal loads, stability, and he says there's maximum moment. And I'm saying that's time theoretical 0. So let's assume that this loading, we've frozen the time and we're now analyzing it. And you can see that there's a wave pattern as it's shrinking to, imagine something, the load is shrinking so small, the wave is approaching this direction, it comes to the center of the wave. The loadings are equal here, and that would be distributed thus, creating the 3 troughs, a ring and a center with a dip in it. Now, when we release time, the first thing that happens is this load shifts. The loading shifts, the stability can't be held, and the loading shifts. And Lewe's work proves which direction this shift occurs in and why it occurs. And you'll see that in the breakdown of the coefficient tables, but that's for later. Just assume for now that we've proven that the load gets distributed in this direction. It doesn't sit like this, it changes. And what that does to the wave is it creates this distortion of it at the center, where you've got the double peak occurring in the trough. You've got 2 troughs alongside each other. So there's a false peak there, if you like. And so the wave takes up this shape as it tries to restore itself to wave and trough, which should be its natural state. So I've said this is as in condition 2, as Lewe calls it, I've called this the unbalanced load with showing instability and the wave motion or the celerity meters per second, that this has moved, that there's some distance of motion in a duration of time, and that's the maximum moment of bending. The next moment, in condition 3 at the center, he shows stability again, what it looks like. We've returned back to this situation, peak and trough, nicely distributed loads, but we've got this clockwise moment of torque, which has been created here. Lewe shows that as a balance force, which is right. I've shown it that there's a force on it here, because there's a double trough alongside it. So the force is greater in that clockwise vector. Okay. And so we've got stability, but we have a clockwise vector now. So what will that do? Well, when the motion of the wave is to switch, as it's shrinking, this center goes up and down. Pop, yeah, it should go up and down. And here it's gone from down. I push my finger into it. And here, it's gone up, which is the natural cycle of the ebb and flow of the wave. But this has now got an anti-clockwise moment of torque applied to it as an equal and opposite reaction to this moment of torque which was applied here. And that has another effect. And it moves to position 5. And you can see this is Lewe's final line on his little diagram. It looks like that. From above, this is what we've ended up with. That the motion has created in the center now, there's not room for one dot. The center is now 2 dots, 2 widths. And you have a crest and a trough within the center of that wave pattern. And therefore that's going to create an anti-clockwise rotation at the center. And so that the real stability, this is stability in reality, where time can never equal 0. It's the resultant of forces, is a rotation anti-clockwise at wave celerity c meters per second. And so this system creates stability at the center. If you look at the net, where this is going at the next moment will be to create that, but with its force intact. So that when we measure it and look at it from our perspective, we can see this, we can say rest mass, nothing is moving, we can analyze it in that basis, but now we know the extra thing. We know that that moment of torque clockwise is maintained by the anti-clockwise action of the wave. So what Lewe has proven is that why is there something rather than nothing? It's because the motion of a wave must be conserved, and he's proven that the conservation of the wave celerity in an anti-clockwise direction preserves a clockwise stability for the entire system. And I think he deserves a round of applause for that.